Alright, so I've collected my data for the collisions lab, and it's now time for me to analyze the data. Remember, the main goal of this lab is to check, is momentum conserved in these collisions, and is kinetic energy conserved in these collisions. Remember, momentum should be conserved in every one of these collisions, and if kinetic energy is conserved, those would be elastic collisions. Now, if I look at the analysis part here, when I have the momentum and the kinetic energy table, I'll see that there's a lot of calculations for each trial. I need to calculate the momentum of both carts before and after the collision, the kinetic energy of both carts before and after the collision, the total momentum before the collision, the total momentum after the collision, the total kinetic energy before and after the collision, and then the ratio of momentum before to after and the ratio of kinetic energy before to after. That's a lot of calculations. There's actually ends up being 12 or 14 calculations per trial, and then I need to do this for 6 trials. So I could get out my calculator and start punching in numbers, but that's going to take me some time to do that. And the likelihood that I make one mistake in this whole set of tables is probably pretty high. So I want to set up formulas in order to do these calculations for me. Now, the first one I want to do is calculate momentum, and I want to calculate momentum for both carts before and after the collision. So in order to calculate momentum, I'm going to take mass times velocity. Now, the one thing I note is that I have the blue mass here and the yellow mass here. So every time I want to pick the blue mass, I'd want it to multiply by this cell. Every time I pick the yellow mass, I'd want it to multiply by that cell. There's a trick to telling Google Sheets that I always want to use this particular cell in my multiplication. So if I'm going to do mass times velocity, I'm going to equals. And then in order to tell it that I always want to use this cell, I'm going to click on it, but then I'm going to add something to it. And I'm going to add a $ before and after the B. And then I'll do multiply by velocity. What that does is it says if I calculate this, or if I change this or copy it somewhere else, it says I want to always use B4 as the mass. And I could even do drag across and it's always going to pick B4. Remember, when I copy down, it changes all the cells down. What the $ do is freeze that cell to be B4. I'm going to do the same thing for the yellow cart. B5. I always want mass to be B5 and then multiply by initial velocity. Or initial momentum, initial velocity. Then I can calculate the final momentum. And then here at the end, total momentum before the collision. Well, that should be, the momentum of the yellow cart plus the momentum of the blue cart before the collision. Total momentum after should be momentum of the yellow cart plus momentum of the blue cart. And then the ratio we're looking for is my final momentum over my initial momentum. And so there we go, I have my analysis. Now, once I've set up this data table, once I've set up these calculations, one of the cool things I can do is just copy these to every row, and it does that calculation for me. So what I'd be looking for to see if momentum is conserved is that this ratio should be pretty close to 1. If it's something less than 1, that says that there's less momentum after the collision than there was before. If it's something greater than 1, that say there's more momentum after than there was before. I would think greater than 1 is probably pretty unlikely. I would think less than 1 is probably a lot more likely. If I look at all my numbers, the one that is the smallest is a little bit less than 0.95. That would tell me about 5% of my momentum was lost in the collision. That's within the range that we would say these are probably the same. And my largest one is 0.983. That tells me only about 1.7% of my momentum was lost in the collision. So I would probably say from my data here, this looks like momentum is conserved. Now I'm going to do the same thing for kinetic energy. And I'm going to plug in the kinetic energy formula. And kind of like I did with momentum, I always want to pick the mass, the blue one for all the blue ones, times V squared. I don't want it to fill all the way down because I want to change this one to be mass of the yellow one. It's V squared, so I have mv squared. And then I want to do the same 2 calculations I did here, that I have initial doing something funny there. There. Total final. And then ratio. There we go. And then I can drag that across and copy that to all the cells. So kind of like the momentum is conserved, what I'd be looking for if kinetic energy is conserved is numbers that are close to 1. Some of these are clearly not close to 1. If I look at trials 3 through 6, for me, those ones are not close to 1. These ones are not conservation of kinetic energy. The two that are pretty close to 1 are 1 and 2. They're both looking like we lost maybe about 8-9% of the energy. But in terms of conservation of energy or energy conservation, these two are the closest to energy being conserved. If I had to guess which ones were elastic, 1 and 2 probably are my ones that are elastic and the other ones are not. So I'd say from this data, it looks like kinetic energy, well, is not conserved in all my collisions. And in fact, in some, it's not only not conserved. Here, I've lost, well, 65% of it to get 0.35. So that's how to do the analysis part of this lab and what you're looking for when you actually look at your data.